In this video, I will be discussing the types of network cabling and cabling standards. This video covers CCNA Objective 1.7. Select the appropriate cabling type based on implementation requirements. Network cabling is an aspect of the physical layer of the OSI model. There are many different types of cable that can be used on a network, and choosing the right cable depends on the distance that must be traveled, the environment in which the cable will be used, the bandwidth or speed that's required, and of course the cost of the cable. There are IEEE 802.3 Ethernet standards that support different types of cabling and cable lengths. Again, selecting the right type of cable is critical in network design. Now, one of the first decisions a network designer must make is what type of cable is most appropriate. And there's two major categories of cable. We have fiber optic cable or copper cable. Actually, some cables also use aluminum instead of copper in their core, but for purposes of this video, I'll use just the term copper cable to refer to all metal core cable. So we have fiber optic cabling and we have copper cabling. Copper cabling itself comes in two different versions. There's unshielded twisted pair, or UTP, and shielded twisted pair, or STP. STP cable is very rarely seen in Ethernet LAN environments because it's very expensive and is typically only seen in harsh environments where the shielding is needed to prevent interference. Cables come in different grades and types that vary in their ability to support faster speeds. The grades of UTP cable are known as category or CAT grades. The higher the CAT number, the higher the grade of the cable. It's important to memorize these key attributes of the different types of cables, so take some time to study the maximum length, the type of media for each cable type. Notice in this chart that the fiber optic types of cable at the bottom three rows, the multi-mode and single mode fiber, can support maximum lengths of much greater distances than any of the category types of media, which are copper cables. The IEEE defines the 802.3 standards for the various cable specifications. Again, take time to memorize each of the IEEE standards, its maximum speed, its name, both the common and IEEE name, the material used in construction, either copper or fiber, and the maximum length that they support. Now, there are some hints that you can use to make this a little bit easier. The number that's before the word base in the IEEE name refers to the speed that the cable will support. 10 being 10 megabits per second for 10 base T, for example, 1000 being 1000 megabits per second in 1000 base T as another example. And we also have gigabit speeds like 10 G base T for 10 gigabit speeds. Also, all the IEEE names that end in a T are using some type of twisted pair cable or copper cabling, and the IEEE names that end with an X or an LX typically use fiber optic cables. Also, one other hint, all copper cables are limited to 100 meters in length. So again, take some time to study and memorize these standards. Now let's start taking a look at the construction of the different types of cable, starting with fiber optics. Fiber optic cables consist of a very thin strand of glass or plastic through which light can pass, and this is surrounded by a cladding and then by an outer coating. Bits are sent across the cable in the form of brighter and dimmer pulses of light to represent the binary ones and zeros. The advantages of fiber optic cable are it allows for much longer cable runs than copper cable, as we saw in our standards, and fiber optic cable is immune to electromagnetic interference, or EMI, and radio frequency interference, or RFI. Now, there are some disadvantages to fiber optic cable as well, and the disadvantage is usually the cost and how fragile the cable is. The equipment used for transmitting on fiber optic cables can sometimes be fairly expensive compared to copper cabling, and also the installation cost, due to how fragile the cable is, can be expensive. Because if you bend the cable too tightly in a small radius or you pull on it, that can break the core inside, and that would prevent it from working because the light pulses would not be able to get through and the cable would have to be replaced. Now, UTP cable is the most prevalent cable used on local area networks. It's relatively inexpensive and easy to install. However, the disadvantage of UTP cable is that it's sensitive to EMI and RFI. Sources of EMI can be motors, heavy machinery, and fluorescent lights. RFI can come from powerful radio transmitters, so care needs to be taken when installing UTP cables so that it does not run close to these types of interference sources. The ends of UTP cable are terminated with something called an RJ45 connector. And as I mentioned earlier, UTP cable, like all copper cables, are limited to an unrepeated length of 100 meters. Here we see an example of a UTP cable RJ45 connector that's terminating the end of the cable. Notice that this 8-pin connector aligns with the pins in the RJ45 port of the network interface card of a PC or of a switch or router. UTP cables consist of 8 individual wires that are twisted together in pairs. Each wire has its own color-coded insulation wrapper. Then all the wire pairs are bundled inside a sleeve of PVC insulation. The twisting of the wire pairs helps prevent electromagnetic interference and something called crosstalk. Now, we've discussed EMI sources on the previous slide. Crosstalk is interference from the electrical current running through the adjacent wires. The twist in the wire pairs break up the magnetic fields of the wires, which reduces the possibility of crosstalk. The color coding of the individual wires is important. There are 2 standards that define the color order or sequence of the wires when they're installed in an RJ45 connector. These are the TIA EIA 568A and 568B standards. The color sequences start with pin 1 and go through pin 8. Take a few minutes to review the color sequence order of both standards. If we wire both ends of a cable to the same standard, we create a straight-through cable. If we wire one end of the cable with a 568A standard and the other end of the cable with the 568B standard, we create a crossover cable. Straight-through cables are used to connect dissimilar devices, like connecting a host to a switch. By using the same color order sequence standard on both ends of the cable, the transmit and receive pins of the 2 devices are connected. For example, in this diagram, the transmit pins on the host network interface card are pins 1 and 2, and they connect to the receive pins on the switch Ethernet port, which is also pins 1 and 2, so we're connecting transmit to receive. And then notice that the receive pins on the host network interface card are pins 3 and 6, and they are going to connect to the transmit pins on the switch, which are also pins 3 and 6. So again, we're connecting receive to transmit. Note that in the 10 base T and 100 base T standards, only 2 pairs of pins are used, pins 1, 2, 3, and 6. In the higher bandwidth standards like 1000 base T, all 8 wires are used simultaneously for transmission and receiving. Crossover cables are needed when we connect 2 like devices together, such as 2 switches. This is because they both transmit and receive on the same pins. So by using the 568A standard on one end and a 568B standard on the other end, the wires inside the cable are crossed so that the transmit pins on one device actually end up connecting to the receive pins on the other device. Typically, crossover cables are needed to connect like devices. However, there's an exception to this rule. Many devices today have what's called an auto MDIX feature, which allows the device to change which pins it uses for transmitting and receiving. This allows the user to connect either a straight-through or a crossover cable, and the device will adjust its pins to work correctly.